Alright, now we come to see with the ESI-MS detection. So this is about electro-spray ionization, ESI. And we talk about this schematic diagram of the setup of a typical CE hyphenated ESI-MS. So that's a CE where you have separations, and after that the capillary channels, right, to this portion there where you have a shield liquid line and a shield liquid pump. So the question is about why we need to have a shield liquid, as we know that CE uses a very minute sample, and we have the samples always in an aqueous liquid state. Too little liquid from CE will causes instability when you have a mass spectrometry in the electrospray, right? There's not enough liquid to spray out, and that causes irreproducible results. So here we have an ESI needle here. Later on you will see how this sample is being injected, right? Now this is a very good diagram, right, to show what are the different components in the CE-MS there. So this electro spray ionization mass spectrometry, right, in short ESI-MS, first described in 1984, become one of the most important techniques for analyzing biomolecules like polypeptide, proteins, oligonucleotides, because they have a molecular weight of 100,000 Dalton or more. So this method, right, is also more and more applicable to characterize inorganic species and synthetic polymer. And we know from the first CE lecture that John Venn and Koichi Tanaka shared the Nobel Prize in 2002 in chemistry for this reason, right, for the development in the soft desorption ionization methods like ESI. So here, ESI takes place right under the atmospheric pressure and temperature in this apparatus. Solution of the sample is pumped through a stainless steel capillary needle at the rate of a few microliters per minute, and then the needle is maintained at several kilovolts with respect to the cylindrical electrode that surrounds the needle. Then the result charged spray of the fine droplet passes through a desolvating capillary, where the evaporation of the solvent and attachment of charge to the analyte molecule takes place. And as the droplet becomes smaller as a consequence of evaporation of the solvent, the charge density becomes greater until, at the point called the Rayleigh limit, the surface tension can no longer support the charge. And here a so-called Coulombic explosion occurs, and then the droplet is torn apart into several smaller droplets. And these little droplets can repeat in the process until all the solvents are removed from the analyte, leaving a multiply charged analyte molecule. As we see, if we didn't have the shield liquid, right, then you will only have the buffer with the analyte here. There's not much you can spray out. Okay, so because of evaporation of liquid, we need to have some shield liquid here to compensate for the lower volume. You want it to have a very high flow rate. Without this, your buffer which has a high ionic concentration, the flow is very slow. Okay, but the problem is because you have a higher volume now, so it causes dilution. When you have a dilution, means you have a reduced sensitivity. Another diagram for you. So typically your flow rate with an ESI-MS detection is about 10 nanoliter per minute to as high as more than 340 nanoliters per minute. The good thing is, here you can have a porous section made by etching. This is the background electrolyte here, and you see that this is a very narrow capillary. I think the key thing is about why it has to be a stainless steel cylinder. Right. Some of the times you have ions, anions, cations there. They may adsorb to the surface. This is something you want to avoid at all costs to make sure it's producing high sensitivity data. Okay, but due to the narrow capillary, right, it's also prone to blockage. Another diagram here, I think the key thing to note is really about how precise this microengineering causes the microfluidic movement of liquid. It's like the small 50 micrometer of internal diameter is extremely hard to achieve. A lot of precision engineering involved here. So as chemists, right, we are chemists by training, we don't have to look in so deeply on the engineering parts, right? But as a whole, first I want to summarize that this instrument is very expensive, right, and it's a very complex geometry, which means to say that if there's some error or if there's data that looks a bit off, I don't think a chemist can repair so easily. Regarding CCD, so as you know, we have a contactless conductivity detection, two-column detection mode. So what happens is you have the actuator electrode and then a pickup electrode placed around the separation capillary. Okay, so this capillary, we use the very traditional ones like the fused silica or even Teflon, but they must be non-conducting, because here we're looking at the conductivity. So that means there's a change in the potential. So imagine if your capillary is conducting, then it will just affect the result. This kind of a complete C system, right, are just sold by several instrument companies, and more than 2,000 companies, right, offer supplies and accessories for this. And the initial cost of this CE expensive maintenance is much higher than those for ion chromatography and atomic spectroscopic instrument. So therefore, all these commercial C instruments, right, with standard absorption of the fluorescent detector, cost in the range of 10,000 to 75,000 US dollar. Now, of course, here you see there's a mass spec involved, right? When there's mass spec, it's even more expensive, right? It could go up to a high 5-digit or even a low 6-digit sum. So this diagram shows you the C4D, the capacitively coupled contactless conductivity detector. We're using this term again later on. Now just note the advantage here. This is a drawing using more physics, but as chemists we don't need to pay attention. Advantage is simple instrumentation, low cost, no need for precision alignment, right? And no need to have contact with solution. This is one of the key points. No need to remove polyimide outer coating, so it's less fragile. Now how does it work here for the C4D? So first we have a transmitter signal, right? You subject the sample around it with high amplitude. Okay, pulse it. And then you have this middle electrode there, C4D, right? That will attenuate an AC signal, right, at the receiver end. So it's more like a middleman, right? You have the transmitter, and then in the other side you have the receiver. What you speak and then you listen. And then the size of this receive signal, the receiver, right, is caused by the change in the conductivity of a sample. So it's about ions conductivity. And then because with AC, so we have the positive and the negative amplitude. It's not so easy to read here. They will be deconvoluted, right? That simplify into a more of modulus amplitude in a DC manner, so that we can see and do data collection. And this is a similar principle as your weighing instrument, your weighing machine. How you weigh yourself, right? How come why will you put a certain weight there? And then it causes a number of 1.02 grams, right, on the analytical balance. It's all about the conductivity detection. Because when you have more pressure, you have more conductivity, and that gives rise to a certain calibration. Another diagram, so more simplified, transmitter, right, middle, electrode, receiver. Okay. Now, key thing is, right, the C4D electrode does not make contact directly with the sample. Very important. How come? Because the liquid, your sample is liquid, and your sample contains ions there. And most of the time, we analyze cations, and electrodes are metal. What happens is you may have kind of a fouling. Fouling means we have metal-metal interactions there that causes the surface to no longer be clean, right? And data may not be reproducible. Here, these are some CE electrophoregram to show the usage of the UV and the C4D detection for sample concentration of 0.1 millimolar. Okay, with a mixture of these cations there. And then you have also another one which analyze until 10 ppm, right? Because we're using UV, right? Inorganic anions as well, not just cations, etc. Hope you can understand why the migration time is such a manner. Okay, 10 ppm. Here we have a UV detections, right, at 200 nanometer absorbance wave number, analyzing TCM herbs. I want to highlight that this is done by research work from Professor Lee, your lecturer, and the co-workers, my senior, right, some time ago. Breakthrough work. Okay, so we can look at it and put up a library to detect potential herbs, right? Do they correspond to the same migration time in this separation method? Then we can see it's does it contain is it a banned substance, your hyperconectin, or is it aconitine, etc. So another example is that we can analyze a basic drug. In this case, we have a pick one that's the indirect UV method, the signal, tramadol here. Okay, and this is pretty common in typical UV detection. So you see a lot of peaks going down and up. Doesn't look very exciting, but what you care more is really you see the signal that you want. Yeah. Some applications. So for laser-induced fluorescence, right? What we can do is sometimes when we tell a species of animal, it's very hard to tell the gender. But in this case, right, if you are able to look at the genes of the birds, right, you can use LIF to identify whether it's a female or male. What happens is, right, in this case, right, if it's a female bird gene, right, you apply the same CE parameters, same buffer, concentration, additive, internal diameter length, right, and the same detection. So 48 nanometer for excitation wavelength, 512 right, nanometer for emission, and they see that the signal for the female shows 2 peaks over here, when the male shows only 1 peak. So what it means is, right, if you have an unknown gene, you want to do some elucidation. This is one of the methods you can do. Again, highlighting Prof. Lee's work. Next, what can CCD-MS do here? So back to the sample of TCM, right? Remember that research a few slides ago. Here we can look at, right, also the migration time of these ions now, because now they're charged, that's why they can move, right? But they came from the different substances in these Chinese herbs. Okay, so in summary here, we have a look at in this topic how we can inject the sample, right? Many two ways of electrokinetic method, hydrodynamic method. Under hydrodynamic method, there's also a few sub modes: pressure, vacuum, gravity. And also in the second part of this lecture, we speak about the detection method, which are more common, the pros and demerits of different methods, but the sensitivity as well, and some application. So with that, I will see you in the next lecture. Cheers.